Okay, welcome back, everybody. Now you have your second plenary that will given by Professor Yang from School of Physics, Zhejiang University, Hangzhou, China. Thank you, Professor, for accepting our invitation. Then you can start now.
Well, first, I would like to thank the organizer for the kind invitation. And I apologize that I could not give the talk on site due to a conflict of schedule of another obligation. I canceled my trip at the last minute. I can see everybody on site is very happy. So I wish you enjoy the event. And I really appreciate that the local organizer can arrange this opportunity to let me to give a talk online. And today I would like to introduce our recent study on the quantum topology of light. And first, I would like to use an example of a Chinese character to introduce what is topology. So Asian Chinese, they use a graph, character to as a language. It is called oracle. It's basically, to carve what you want to express on the bones of animals. And for example, if you want to tell people about the tiger, the easiest way is just to draw a tiger, more or less. And we can see that it contains a lot of details, including the claws and teeth and, all these stripes. Of course, this is very good because people will not mistake this tiger with a dog, for example. But on the other hand, it's very complicated. You must draw every detail every time. So later people find that maybe, we already agree with something of this tiger. So let's just simplify. And you can see later it's simplified to keep just, not so much detail. And then they just keep the skeleton, without confusion. But the different people still write tiger in a different way. This is vertical. Maybe somebody will write it in horizontal way. So they adopt some convention. That is to write tiger like a square and to write every Chinese character in a square shape. So from the second to the third to the fourth step, we can see that basically they don't cut one part or reduce some part of this character, but just make a continuous deformation, stretch one part and compress the other part and make this continuous transformation. So we call this topological transformation. And just, test you what you learned from this example. I give you another example. So anybody can tell what is this? I think many of you will guess this is a cat. Of course, it's very similar to a cat with a round face, 2 ears and 4 legs. But the cats did not exist when this kind of oracle were invented in China. They were pets imported from outside. And what this character really mean is this thing, It's called a ding, basically a pot. It also has 2 ears, a round face, and 4 legs. Well, we can use a symbol to represent actually both of them. And we call this is topologically equivalent to each other. And now we come back, to the real academic things. And topology was a concept from mathematics. It describes the property that is kept in a continuous transformation or deformation. Like, we can continuously change a cup to a torus. And during this transformation, we always have a hole in this, in this manifold or in this closed surface. And later in the 1980s, people found such concept also exist in the band structure of a lattice. So we find that if we calculate the so-called Berry curvature of energy band of a solid, most of the time you are going to obtain zero, of course, but for some special materials, later, we call that Chen insulator or topological insulator. After the calculation, you are going to find some of the band give you non-zero numbers. And between two bands that have different chain numbers, you have these topological chiral edge states located at the edge. And these contribute to the quantum Hall effect. Now this kind of topological material already become a very big research area in condenser matter physics. And just by extending this concept to optical system, to the classical photonic crystal, people found such kind of chiral edge states which only propagate in a definite direction, not in the opposite direction. We can have similar thing for light, such that we can have unidirectional waveguide. So this was already found like 15 years ago, or even earlier. And but this is a classical, effect of the light wave. So we asked the question: does light quantization lead to new topological states that could not be explained by classical optics? And in this talk, I would like to just introduce to you some of our results in this direction. I would like to start from Haldane work in 1988. He found this first condenser matter model without a big magnetic field, such that you have lambda levels, just by introducing periodic magnetic field in this lattice structure, such that you have nearest neighbor hoppings between the lattice sites that are attached with a certain phase, a gauge phase actually, due to this periodic magnetic field. You can find the band structure of this basically a graphene structure. Will give you a different chain number in the conduction and the valence band. And the result is that there's going to be a edge state connecting these two bands. That is actually a basic principle in topological physics. Once you find in the bulk energy band different chain numbers, you are always going to find the edge states that are connecting these two bands. And and these states located on the edge, and the only propagating in a certain direction. And this is called a bulk edge correspondence. And Haldane, after the publication of this paper, he has been trying to find, a way to realize it. Of course, it's very difficult to realize it in condenser matter physics, but finally he succeeded in proposing a optical realization of these chiral edge states or quantum Hall edge states. So I think he already had this idea before 2005, but the paper was only published in 2008. So that was a struggle, but this was the first paper of topological photonics. So by just making analogy between, photonic crystal and electronic crystals, he was able to find, we can actually break the time reverse symmetry, and we can have chiral edge states. And just 1 year later, people realize these, quantum Hall edge states in microwave lattice. They demonstrated that at the edge of the lattice, there's a unidirectionally propagating edge mode. And if you have some obstacle over here, the light pulse is not going to be reflected, but it will go around this obstacle. So this is like reflection. It's a backscattering free propagation. And later, people realized similar effect in photonic waveguides, and a lot of similar physics in many optical materials like metal materials, silicon photonics. People also studied the PD symmetry topology and many others in this field, and also extend this to quantum photonics by introducing a quantum light source. So all these kind of study became possible because there's some similarity between the Maxwell equation and Schrödinger equation. For certain case, actually we can write them exactly the same as each other, but just replace the time dimension with one of the space dimension, and the refractive index will play the role of the potential. So this research become possible because of this similarity. This means that all these property actually were classical property of light because it's based on Maxwell equation. It has nothing to do with the second quantization. We don't need to have photons to demonstrate this effect. So, we also the question I asked at the beginning, and all the story actually began with a note given to me by Professor Renbao Liu from the Chinese University of Hong Kong when I was a PhD student of his. And he, at this very early time, proposed that maybe we can find some quantum optics model to simulate kinetic matter physics. And the idea is that to use the Fock space of light and use the photon number, as labels of the lattice size. And he was able to, propose some preliminary example to do the simulation of the Holland model and several other important models in kinetic matter physics. And later, in collaboration with Marlon Scully and Xiao Zhu and many others, we were able to, propose to use the superradiant states of collective atoms to do such kind of a quantum simulation. But this is a little bit different from what Renbao proposed. This is to use the collective excited state of atoms. But later we came back to Renbao's proposal, and we realized that by using the photon number states, we indeed can find the lattice structure of the Fock states, and we can do quantum simulation based on these Fock state lattices. And this is what I'm going to introduce in the next. First, I think to make a clear difference when we compare the study we are doing with those people has already done in topological photonics, we must first identify what are the classical degree of freedom of light and what are the quantum degree of freedom of light. So this is a general expression of any light field. And there are some of the degree of freedom here, like the mode function, spatial mode, and the frequency, and the wave vector and polarization. These are, the degree of freedom that are determined by the Maxwell equation. Once you write down the Maxwell equation, you solve the problem, you find you must have all these, physical quantity to be determined. There's only one exception, is the light field amplitude. So when you try to determine the amplitude, you will find that there's a quantum fluctuation over there, and instead of using a constant number, we must introduce a quantum operator, the creation and annihilation operator. And this operator lives in the space of the so-called Fock space, and they are off-diagonal operator in this space. But this kind of space, provide us additional degree of freedom to compose lattice structures. Of course, in order to find or to investigate this lattice structure, we need a strong coupling between the atom with the cavities. And here, just to show you example of a GC model, and we can actually write down the Fock space, the Fock states that are coupled by this Hamiltonian, by the GC Hamiltonian in a lattice structure. Well, you might ask, this seems like we are making a simple question more complicated, right? So we can solve a GC model very easily. Why should we look at this problem from a very complex structure like phase? I just give you one of the motivations. So let's come back to the GC model. In this audience, everybody, I think, has learned this model. We put an atom in a cavity, and they are on resonance. We use this Hamiltonian to describe the interaction between the atom and the cavity. And the energy spectrum of the GC model is just something like this. If you have vacuum field and atom on the ground state, you have zero energy. So in the rotating frame, if you have one photon, you are going to have plus and minus G, where G is the vacuum-Rabi splitting of the energy spectrum. And if you have two photons, you have square root of G. And so the energy spectrum have this square root of n scaling over here. Let me give you another example from the graphene physics. So in graphene, you have Dirac cone, and if you apply magnetic field to this material near the Dirac cone, you are going to find the Landau levels, and different from free electrons, where the Landau levels are equal distant with each other. In this at the Dirac cone, you are going to find the Landau levels have a very peculiar square root of n scaling. So now you are going to find the similarity, right? And people in this field from very early time find that to solve, this energy spectrum, they can transform the graphene Hamiltonian to a GC model Hamiltonian. So by just introducing this operator, annihilation operator, you are going to find the energy spectrum of this, graphene in a magnetic field has exactly the same form with the GC model. But the problem is that we could not understand it. So these two models are totally different from each other. So one is a cavity QED model, the other is a condensed matter model. They have no relation with each other. But after this talk, you're going to find they are very, very neatly connected with each other, and we are going to find the correspondence behind this, equivalence. So all the physics I'm going to talk is based on a multimode GC model. We can have, not one cavity, but 2, 3, or 4, or 5 cavities. Now the atom is connected to multiple cavities. Of course, you can have other complicated configurations, but now we just constrain us to this very simple single atom, but multiple cavity GC model. So think about this. If you have an excited atom and it's coupled to these 3 cavities, and we have different photon numbers in the cavities. So where should the atom emit the photon? I mean, to which cavity? After very simple calculation, because the annihilation operator, creation operator property, the coupling strength is proportional to the square root of n plus 1, where n is the photon number in the cavity, we might reach to the conclusion that the atom more probably will emit the photon to the cavity, which contains more photons, or the most photons. Of course, that is because bosons are social, they like to stay together. But, these two cavities, if they combine together, they might obtain the photon instead. So this is a very complicated game. The cavities are trying to compete to get the photon from the atom. So in order to make the phase simple, let's just go back to the Hamiltonian. So now I just write down a very simple multimode GC model, and the mode number is D. D can equal to 1, 2, 3, 4, or 5, and any numbers. And we have a total excitation number N, which means how many photons in the cavities. So N can be any number as well. And we use this circle to denote the atom in the ground state, and the square to denote the atom in the excited state. And we have 3 or 4 or 1 number on each side to label the photon number in each of the cavities. We go back to the single mode GC model, which is very simple, pairwise coupling between each other. And the coupling strength is proportional to square root of n. And n is the photon number. So we can have thicker and thicker coupling lines between them. And if you have 2 modes, the photon can be in each of the cavity, so you have 2 states, 1, 0, photon in the first cavity, and 0, 1, photon in the second cavity. But all these 2 states is coupled to the state the atom get excited and no photon in both cavities. So the 3 states are connected in this way. And if you have 2 photons, you have 5 states coupled. And if you have 3 states, you have 7 states coupled in a line. And now if you have 3 cavities, on each side you have 3 choice. So if you have more photon number, you are going to find what I have shown you, more like a graphene structure. And if you have 4 cavities, you are going to have a diamond structure with different lattice size, depending on the photon numbers you have. And if you have 5 cavities, you are going to find a 4-dimensional lattice. And the 6 cavities, you are going to find a 5-dimensional lattice. So you can use this method to build multiple high-dimensional lattices as high as you want. But let's just go back to the 2-mode GC model, which is the non-trivial model, the simplest non-trivial multi-mode GC model. And now I give you a lattice which is much longer than I have introduced. So now we have 15 lattice sites. And on this side, we have 15 photons in the first cavity, and on this side, we have 15 photons in the second cavity. Okay, so what is the property, the basic feature of this lattice? It has site-dependent coupling strengths. We have 2 kinds of coupling strengths. One due to the photon number change in the first cavity, the other the second cavity. So here, for example, this T1 is proportional to square root of 15, and the T2 is proportional to 1, and the square root of 14, and the square root of 2. And if you go to the right side, you are going to find T2 is proportional to square root of 15 now, and T1 square root of 1. So their relative strength changes across this lattice. In the middle, they equal to each other. And this is very interesting from a topological perspective, because people back more than 40 years ago already found, well, if you have this relative strength change across your lattice, you are going to have 2 different topological phases on the 2 sides of the lattice. The relative strength between T1 and T2 determines the topological winding number of this lattice. Is just a terminology, not very important, but just simply, you just need to know, well, topologically they're different. And due to the principle we have introduced at the beginning, the bulk edge correspondence, if you have 2 different topological material, there must be a 0 energy mode located at the edge of these 2 topological phases. And this mode only occupy one of the sublattice. This was already found more than 40 years ago. So now we have a Fox state lattice that has 2 different topological phases on the 2 sides. So we expect there's a topological 0 energy state over there. And this is the topological 0 energy state. Now, how could we find this state? This state satisfies every criteria of what people have found 40 years ago. And it's very simple to find this edge state. We just need to combine these 2 cavity mode to form a bright mode. And this bright mode is coupled to the atom. And we have another dark mode, which is orthogonal to this bright mode, but decoupled from the atom. Now we can redistribute the photon number in B1 and B2 mode. not in A1 and A2 mode, which is the lattice structure, but if you redistribute the photon number in B1 and B2 mode, you're going to find that the thing is very simple. We can have 15 photons in the B1 mode and 0 photon in the B2 mode. And the 15 can become 14, while the dark mode does not change, and the coupling strength is square root of 15. And we can have 14 photons in the bright mode and 1 photon in the dark mode. Now the coupling strength is square root of 14. And we can continue to count and until we have 1 photon in the bright mode, and then the coupling strength is square root of 1. So now we can see all the states are pairwise coupled, but we have one state left. That is when all the photons are in the dark mode. And now we don't have any photon in the bright mode. So we have a 0 energy state over there. And if you transform this dark mode into the basis of the A1 and A2 mode, you're going to find the wave function I have just shown you. And if we, add another mode, cavity, to the system, we are going to have this 3-mode GC model. And here I draw a lattice structure that contains 20 photons. And in this lattice, we have similar property on the edge, on the vertices. You are going to find the coupling strengths are very different from each other, while in the middle, you're going to find that they are more homogeneous. And for a long time, we could not find the reason until about 10 years later, we found, well, people have studied this kind of problem in a stringed graphene. So if you put the graphene on the substrate, and there's going to be, inhomogeneous string in the system, and there's going to be some physics over there. This is unstrained graphene. It has Dirac cones, and if you apply strain, there's going to be deformation of the band structure, and most notably, is the Dirac cone are going to move in the Brillouin zone. And if the string is large enough, 2 Dirac cones can merge and open a band gap. This is called a LPHYS' topological transition from a semi-metal to a band insulator. So how to observe this, and when will this topological transition happen? It turns out it only depends on the relative strengths between the coupling strengths. So if these coupling strengths can form a triangle, that is the summation of the 2 coupling strengths is larger than the third one, we are going to have a semi-metal phase. Otherwise, we are going to have a gapped insulator. So the question becomes, where in this lattice can we have a band insulator, and where do we have a semi-metal? We can already judge in the middle it's a semi-metal, and in the vortices there's going to be the band insulator. But where is the boundary? If you put the number, put this relation, and put the number into this relation, you're going to find the boundary. The boundary is on the inner circle of this triangular boundary of the Fox lattice. And within this inner circle, you have a string, and this string has been found that to have a magnetic field effect. And people already found, this kind of nano quantization in this stringed graphene structure. So obviously, we are going to, look into this direction. And just by using the same method as in the 2-mode GC model, we can, diagonalize this 3-mode GC model and find that the band structure, indeed, we have a lot of flat bands, and the flat bands have energy scaling square root of n. So this is just what we asked at the beginning. What is the relation between a GC model and the magnetic field and the graphene magnetic field? So now we find the relation. That is, this inhomogeneous coupling strengths give you a effective string, give you a string field, and string has an effective magnetic field effect, such that we can also have this nano quantization, and we can use the relation between this GC model energy spectrum and the real graphene in nano levels to obtain they must be equal to each other to obtain the effective magnetic field in this Fox-Still lattice. And this can be obtained by just put a number into it. And we found that the magnetic length and the lattice constant, the ratio between them is just, a number. And this is square root of n over 2. And n is the photon number in the lattice. So LB is inversely proportional to the square root of magnetic field. So if n tends to infinity, and this just tends to 0, which goes to the classical case. So we don't have any strain in the field, in the lattice. And that is, just the classical problem. And but when n is small, like if we put a 20 in it, we can calculate the effective magnetic field can be as large as 3,000 Tesla. This is very big. And if you put a smaller number, that can be even bigger. And even this magnetic field actually has a structure, in the in circle. It's not uniformly distributed. It has a distribution according to this formula, and we can actually draw every of these eigenstates in the Landau levels. But just it has analytical expression. And in the lattice, they are going to have distribution that's very similar to what people have found in graphene, actually. So this actually provides a new method to study the physics in graphene. And we can observe, dynamics by applying effective electric field to the system, because now we already have effective magnetic field due to this inhomogeneous coupling. And if we detune two cavities, we are going to introduce a linear potential in the lattice. And what will happen is that for initial state prepared in the 0th Landau level, we are going to find this kind of Bloch oscillations. The state is going to oscillate in this zero energy band. And in the lattice, we are going to find the wave function is going to move perpendicular to this applied force. That is just a signature of the Hall response. And it's going to be reflected by the topological edge over here and by the lattice edge over here. If you change the direction of the electric field, you can still find this oscillation, but always perpendicular to the applied force. And we can actually build more complicated model, just the one I have mentioned at the beginning of the talk. The Holden model, we can introduce next or nearest neighbor Hopkins in this form. And what will happen is that the band structure, the flat bands, are going to be transformed to this structure. And all the positive Landau levels become a single band. All the negative Landau levels become another band. And the 0th Landau level become edge states connecting these two bands. And we can see it is chiral, because if you prepare initial state on the topological edge, you're going to find the states going to rotate around this in circle, which is the topological edge of the system. And now I just use a couple of minutes to introduce the experiment. We actually have a collaboration with the superconducting qubit platform group of Professor Haohua Wang in Zhejiang University to investigate, to synthesize many kinds of many-body interactions in superconducting qubits. So I asked him to fabricate this chip for us. And that was not an easy job. He was considering this can just be done in a couple of months, which turned to be a couple of years. And but finally, we did it, and we fabricated this chip and demonstrate that, we can observe these topological edge states and the topological transport. So for the topological zero energy states of the SSH model, we can transport the edge state from one edge of the lattice to the other by changing the relative coupling strength between the two modes with the atom. And we find this experimentally, the initial state on the 0,5 side, then, it goes to 5,0. And in the middle, we can find it only occupy one of the sublattice. And we can make state tomography and to find this is a two-mode binomial state, which keeps its quantum nature characterized by the negativity in the Wigner function. And by preparing initial state on one lattice site and marrying the Rabi oscillation of the atom, we can find this very complicated Rabi oscillation, and then we make Fourier transform. We find this quantized energy spectra. And these are square root of n, scaling. So this is the effective, the pseudo-Landau level. And we can also introduce the effective electric field and observe this, valley Hall effect. The wave function propagate perpendicular to the applied electric field and it goes back. And we can also, by periodically modulating the coupling strength, to introduce a Haldane model, to synthesize a Haldane model and prepare initial state like this, and observe this chiral motion of the edge state. Of course, due to the decoherence, the state, gradually goes inside of this lattice. And I would like to briefly introduce some application of this phenomena. The first one is that we can actually make a quantum circulator of the system. For example, how about if we just keep the Haldane next to nearest neighbor Hawking term in the structure in this Hamiltonian, and by preparing initial state, that's the atom on the ground state or on the excited state as a superposition, what will happen is that the photons are transported to different lattice, different cavities, depending on the quantum state of the atom. So in this way, actually, we can transform a coherent state to different cavities, and we can prepare a quantum superposition of them. So this is like we can prepare Schrödinger cat state in this way. And it also reveals, some hidden relation between some different kinetic matter phenomena that people thought unrelated, like the Valley Hall effect and the Haldane model. So these were considered different because the Valley Hall effect is like, non-topological. It's because of a breaking symmetry, the inversion symmetry breaking. And Haldane model is due to time reversal symmetry breaking. So these were thought as different. But, inversion symmetry is the inversion of space, while the time reversal symmetry is the inversion of momentum. So if we, combine space and the momentum as a phase space, we're going to find that actually they are equivalent. So those are just, can be represented by precession of big spin along different axes. And we can have a combination of these two effects. And also, we can use other system to simulate the Fox-Steel lattice, like we use a lattice of microwave cavities to synthesize the coupling strength of the Fox-Steel lattice, such that we can have a lattice with only flat bands. So you cannot find any dispersive band in this two-dimensional lattice. And this can be done with any lattice size. So at the end, I would like to summarize my talk. This is like, if you look at the GC model in a different way in the Fox state picture, you're going to find a lot of new physics over there. And I think this is just one small corner of iceberg. And if you are interested, you can look into our recent publications in this direction. And I would like to thank my collaborators, experimental collaborator, Professor Haohua Wang, and Jinfeng Deng, and Han Dong, and Cao Song. Yeah, they are experimental team that finally make this idea work. And I thank my other collaborators, in particular Professor Renbao Liu and Marlon Scully and Xiao Chu for the nice collaboration. And thank you for your attention.
Thank you very much, Professor. Now we have time for questions. Is there any questions in the audience?
Thank you for the very nice talk. Correct me if I'm wrong, but in this model, it's different from the SSH because there's no translation symmetry. Because I think every coupling strand changes with index or position, if you like. So, can we? I'm not very sure, but can we still define good bulk or boundary correspondence on this one?
A very good question. Well, the beautiful thing of topological physics is that it doesn't matter, if they change. There's no translational symmetry, of course, in this lattice. But the beautiful thing of topological physics is that only the relative strength of T1 and T2 matters. So it doesn't matter how. So T1 is like 10 times of T2 or just 1.1 times of T2. It doesn't matter. So if T1 is larger than T2, we know topologically this belongs to one topological phase, right? And just this robustness of this topological property allow us still view this lattice as a SSH model. And the same thing also happened in the in the lattice I introduced later, the Howden model, for example. So we have all these inhomogeneities, in the lattice, but it doesn't stop us to observe these chiral edge states. It's over there just because if you calculate the chain marker. So for this kind of lattice, you can use the chain marker to characterize the topological phase. You are going to find the number is definite.
Okay. Dawei, I love these triangular lattices and the dynamics of excitation going around the lattices. But what happens though if you have a triangular lattice, but the boundary of the lattice isn't triangular, but it's rectangular, let's say? What does that change?
Thank you, Barry. So this this boundary is determined by the vacuum state. So I would see in some other coupling form, like if you don't have, this three-mode couple to a single atom, if you couple them in a different way, for example, you just have more atoms and couple with the cavity in different ways, you might have a different edge. So whenever you encounter the vacuum state, you have an edge. So on this edge, the state in the second cavity is the vacuum state. And on this edge, the state in the third cavity is in the vacuum state. So it has edge because we have vacuum state. So photon number cannot be further reduced in this direction. So this edge is determined by this property. So if you have other couplings, like if you have four cavities, and you couple them in a different way, but not couple them to a single atom, because otherwise you're going to have a diamond structure, and it has that four surfaces as edges. You might also, you couple them in a different way. You might also have a triangle, have a square boundary. Yeah.
Thank you.
Okay, more questions? If not, you want to thank you, the speaker again.
Thank you.
Following the program, now you have Professor Anderson Gomes from Universidade Federal de Pernambuco, Recife, Brasil.
So thank you very much. I was asked to stay here for two reasons. One is I can hold myself here in front of this nice audience, and they said that they can get my picture better. So I'll do that. I'll obey. So thank you very much to Vanderlei and to all the organizers for inviting me to give this talk, and we are back to the classical world. And I am going to talk about this wonderful world of random laser and random fiber lasers. Except for the students that were here yesterday, who else have heard or read about random lasers and random fiber lasers? Okay, good. So, let's see, shall I go here? I'm from Universidade Federal of Pernambuco, here in Brazil, only a few hours flight, no delays, everything okay. I did not need to call Vanderlei for anything. Our physics department has about 45 faculty members. 2 of them are here, myself and Cid Araújo, that young guy sitting over there. He's going to give a talk like mine on Friday. So that means I don't have to explain anything. I'll leave it to him on Friday. So I can fly over and give you a lot of information. So this is the picture not good. I don't know why. But this is my group, lots of collaborators. Some of them are here, Denise, Zel, Jean-Pierre Van der Weide. This is the financial support. In our lab, we work on nonlinear optics, on nanophotonics, biophotonics, photonics device, educational activities. And just to give you a flavor on nonlinear optics, the last few years, we have been working on 2D materials, particularly those layered transition metal decoccogenides, and we have done a lot of intensity-dependent studies on optical nonlinearities. We also have done some work with plasmonic gold metasurface. Also in biophotonics, we mainly work with imaging diagnostic in dentistry using either OCT, we have this book that came out last year, and also using photoacoustics. Most of this is still in the lab, but OCT, we have done some work in the clinic. So for today, I'd like to talk about the random lasers, give you a flavor of these, and then random fiber lasers. And then I want to mention about random laser, random fiber laser, and the connection with the Nobel Prize of 21. As I said, I'm going to give just a broad overview. I'm not going to go into some details. Particularly for this third part, Cid will go deep into that. But I want to spend some time on recent results on random fiber lasers for ultra-short pulse generation and also multidisciplinary work. And then, of course, we always ask what's next. So I didn't even need this transparency here, but always nice to remember that we learn that the laser, conventional laser, is a cavity pump, 2 mirrors, sometimes used to be 3 if you want to do those collide pulsing modulog for those in ultra-short laser pulse. But basically we have those, and then the main reason for the mirrors is to provide the oscillation, the optical feedback. Otherwise you have amplification. So back in 68, between 66 and 68, Letakov, he proposed that instead of having 2 mirrors, you could have a scattering medium. And this proposal is a theoretical milestone on this, is his idea. Between that year and 94, few papers appeared from Russian groups and a French group exploiting neodymium micropowders mainly, to generate light that they did not claim was lazy, but stimulated emission was there. In common, all this work used micron-sized powder, and there would be the possibility, even not being spherical, we could have whispering gallery mode. So the first experimental milestone paper where, in an unambiguous way, we explained and demonstrated laser action in strongly scattered medium was exactly 30 years ago. So we can say we are celebrating 30 years of that seminal paper. So in that paper, we had a big neodymium egg, a big optical spectral analyzer. we had this cell where we put a dye, and we excited in this way, because if we excited in another way, the two windows of the cell could act as a cavity. 4% is enough. So we pumped this geometry, and if you look here, this picture, wide one is the broadband at low intensity, and then at high intensity, above certain intensity, which we know is the threshold for the laser, we have the narrowing of the laser, and we also have the nonlinear intensity behavior for the emission. So this happened because we put titanium dioxide nanoparticles inside the dye at the right concentration, and then we could have what Letakov proposed in a very clear way. So a few years later, 5 years later, Hui Chao and a group, they used zinc oxide nanoparticles to show that if you have this powder, you could have the same kind of emission, but instead of having a smooth spectrum like we have here for the laser, which we know now that we are in a so-called diffusive regime, she could see clearly those spikes. And those spikes were explained by having this kind of loops. And this is happening because the scattering length was close to the so-called Joffre-Reger regime, where you can go to light localization or weak Anderson localization. So in this case, you see all those spikes which are signature of the modes of the random laser. Because although you do not have two mirrors, but you have optical feedback, and a characteristic of a laser is that you have optical modes. And this is going to be very important later on. So to summarize, simple definition of a random laser is a coherent optical source where optical feedback comes from light scattering in a disordered medium rather than to static mirrors. So you can see random lasing basically everywhere. You can see you can have scatters inside the gain medium. The scatters can form the medium. You can have those together with plasmonic nanoparticles. You can do this in a colloid, in powder, in membranes, in a chip, and of course in an optical fiber. So there is since 94, there's a big growth in the field, lots of publications and applications. And again, a second summary here is the following. Random lasers, they are mirrorless, but they are not modeless. They have modes. So they are educated lasers, right? They have modes. So the spectrum is independent of resonator frequency because we don't have a resonator in the sense that we have two mirrors. So who decides where it lays is the gain medium. Who decides the line weights, again, is the gain medium, right? There is a lack of tunability in the actionality, which can be managed. And it's Poissonian statistic for the number of photons. So if you look at performance properties, in the last 30 years, everything has been studied in different ways to optimize random laser, threshold, tunability control techniques. It is multidirectional. Directionality control techniques have been demonstrated. Spatial and temporal coherence have been studied, as well as polarization properties. So it has everything that a common laser, conventional laser has. So again, you can see this view graph in this review paper in Progress in Quantum Electronics from 2021. And there you can have all the what happened in the last 30 years, all different kinds of materials and architecture for random laser. I'll just give a few examples. For instance, if you take a crystal, neodymium, in any kind of host, if this is again medium appropriate for lasing, if you crush the mirror with a powder, neodymium has those levels. You look at the 1 micron, well-known emission. Here you see the spectrum, wide spectrum below threshold, and then very thin spectrum above threshold. And here is the measurement. We do this typical signature, which is enough to show that we are lasing, but now and again, we also do the measurement for coherence and so on and so forth. So this is one example, but you can go from bottom up. You can prepare nanoparticles through some chemical process. And again, you can have random laser emission. In this case, I'm showing 5 different excitation energies. where this one, you have several spectrum here, about 20 or so, and you can have it's below threshold, it's in this region here. As you go around threshold, you see the fluctuation is very high, and then above threshold, it fluctuates more than below, but it's less than around threshold, and it's very thin, so this is in the lasing regime. So we're going to exploit and to analyze carefully this intensity fluctuation, and that is going to give us a lot of information. You can have a bio-inspired random laser. If you look at the wing of this cicada, the wings, they have a nanostructure, a bio-nanostructure, natural one. If you put some gain medium here, like a dye, and excite, you're going to have random lasing in the same way as we saw several years before. You can also have it in a biocellulose-based device. So you have a membrane, and then it can be a flexible laser. So we normally don't have that, but in this case, you can have a flexible laser. Again, all these signatures. One question always arises, can we have it electrically pumped? Yes, and that was a paper several years ago. But more recently, this group from Cefe Lopez in Spain, they provided this very, very simple idea. You know, those ideas that you say, why didn't I not think of this? He got a semiconductor laser from a pointer, which has the two mirrors. And then he scratched one of the mirrors, but not scratching like anything. Used a proper femtosecond laser, and he designed and made a nanostructure that was disordered. And then it's random lasing, because there is one mirror, but the other mirror is scattering. So that is 1 year, 2 years ago paper. It certainly is opening up the door for lots of applications, because now you can have a nice electrically pumped random laser. You can amplify with another semiconductor amplifier, everything compact. So this is a good way to go. We could also have a cold atom random laser, which was published by Ruben Kaiser, which certainly is known to some of you. It was done in rubidium atom, and it exploits the Raman transition in rubidium to have gain plus scattering in a given region here. And in that region, where gain plus scattering was playing the role, because that's what you need, then it had lasing emission. That possibility was, that demonstration was important because several years ago, several decades ago, Letakov proposed that we should have astrophysical laser. And the idea is that feedback in that situation is due to scattering. We have the sun as the pump, we have the medium like CO2 or nitrogen, and you have the scattering. So I'm sure Sid is going to work more on that. Regarding applications, we are always asked for applications, particularly when we ask for money. Cancer diagnostics, speckle-free imaging, that's perhaps the so-called killer application. And then we can also have chemical sensing, nanoscale sensing, time-resolved spectroscopy, and so on. We can have optical sensors based on random lasers. It has also been demonstrated. So this is all about what we call bulk random laser in 2D or even 3D. Now let's talk a little bit about random fiber lasers. Random fiber lasers, what you do is you have a fiber, and somehow you have a gain medium in the fiber. It can be a rare earth doped ions. It can be the Raman gain, and you need some scattering. So the first demonstration was done in Recife by our group. What we did, we had a microstructured fiber in the core, which is empty. We put the dye and the nanoparticle. We excited transversally and look at the emission. I'll show a little more. And then a couple of years later, Roman Kashyap used the erbium doped fiber, and in the core of the fiber, inscribed a disordered fiber Bragg grating. So the disordered fiber Bragg grating act as the scatters, and that's the laser that I'm going to exploit. Then Turitz in the UK, they used the Raman scattering and the Rayleigh scattering. And at that time, they needed 80 kilometers of fiber because the Rayleigh is very weak. But I'll show at the end that you don't need that. You need only a few centimeters to have the scattering acting as the optical feedback mechanism. And then by 2014, the group in China, in Chengdu, Zinan Wang and his group did the same work, but using what they call a short fiber, a couple of kilometers. So that's the random fiber laser, the first work. As I mentioned, we have a microstructured fiber. We excite transversally and then look at the longitudinal emission, and that's what we have. Again, line narrowing, threshold, and everything. Okay, so after 2007, as I said, we have the random fiber grating, the Raman plus Rayleigh, again, the Raman plus Rayleigh in short fiber, but we also have a polymer optical fiber using nanoparticles in the core and dyes or different kinds of nanoparticles to have a random lasing in a small piece of fiber as well. So I mentioned that because, again, I'm going to use this kind of fiber at the end of my talk. So more recently, our group did some work on what we call hybrid electronically addressed random fiber laser. What we did is in this piece here, we have a semiconductor amplifier, and if you put a coupler here, this becomes a mirror, a loop mirror. So it's like, and then you have the erbium doped fiber here. Because you are triggering this semiconductor amplifier here, the feedback mechanism comes from this mirror. This is the gain medium, the erbium fiber, and then you can choose a point inside, along the fiber. And this point is determined by the frequency that you use to synchronize your laser, to excite your semiconductor amplifier. So if you do that right, you can have a peak here at about 1.5 for the erbium fiber, and then you can exploit this in any way, in any position you like. That's why it's called electronically addressable. Then we exploit a little more this kind of architecture in these two other papers. But another application for random laser was done in China, again by Zidan Wan's group, where they use a random fiber laser based on Raman and Rayleigh scattering to be the seed for this big laser facility, where they use this with a terawatt facility. To have a good seed laser is very important for the whole process. So again, this is another application for the random fiber laser. So having given you a flavor of random laser, random fiber laser, a couple of applications, what they call multidisciplinary application. Again, I'll go fast on this one to arrive at the last one. So here, I'm going to use this piece of fiber, which is a 30 centimeters piece of fiber. It has erbium in the core, and this cartoon here shows the fluctuation provided by the fiber break grating, right? So if you excite the proper pump, you'll see emission around below threshold, around threshold. Again, we're going to analyze different applications, it's different analogies. And using this fiber, we could study the turbulence, we could study extreme events, blockade states, transition for ferromagnetic to spin glass phase, or paramagnetic to spin glass phase, Levy flight, and more recently, photonic Hall effect. So all of these, by analogy, we can use the random fiber laser and the random laser as a platform to look at all of these effects, which is, again, very nice to do in the lab. So we have a bunch of publications on that. It's good for the students. And then, because of that kind of work, there is a link between what has been done by our group and by a group in Italy to the Nobel Prize in Physics in 2021. So it was given to Manabe, Hasselmann, and Parisi for understanding of complex systems. Two of them, Manabe and Hasselmann, for physical modeling of Earth's climate, and Parisi for interplay of disorder and fluctuation in a physical system, from micro to macroscopic world. So disorder and fluctuation is what we have in a random laser, right? So the first experimental demonstration of the theory behind Parisi's idea is the so-called replica symmetry breaking. Sid is going to explain everything about replica symmetry breaking on Friday, so don't miss it. But what matters for me here is that using random laser, that was the first time the proposal of Parisi was demonstrated in any experimental system. So what is shown here is the signature of what's called Paris parameter, this Q, and the probability distribution function of these parameters. If you are in the so-called paramagnetic regime, you have a single peak at the center for the Paris parameter. But if you are in the spin glass regime, you have 2 peaks, and here is the transition from one to the other. And the analogy here is because the optical modes of the random laser are equivalent to the spin variables in a magnetic system. The temperature in the magnetic system where you go from one transition to another, the equivalent is the inverse of the pump energy. So doing this analogy, Claudio Conte first in 2006, he demonstrated that you can have a glassy random laser, and that 2015 he had all this demonstrated for the first time. And in our group at in Recife, we were working with random laser, and we had people that understood about all of these replica symmetry break and magnetism and so on. And then we demonstrated that this is universal, so we can do that in any kind of different random laser system. So we did it in the powder, neodymium powder, again in a dye, and then in a fiber. We also studied in the same laser, the same system. We studied turbulence hierarchy in the random fiber laser. And in this case, again, same experimental setup. And after we had our results, we had this published, came the Nobel Prize in Physics of 21, 5 minutes. But, okay, if you say so, he's the boss. So, Sid, I think you had some agreement to see him, so I leave this for you, okay? So, but at the end of the day, I'll go to this one. What those guys in that scientific background paper showed is that our work, one of our work, connects the work of the two of the Nobel Prize, Hasselmann for climate and Parisi. And of course, we did not know that. But that was very nice to know. This is all summarized here. Okay, recent advance. Ultra short pulse. Back in '94, right after we did our first work, Alfano excited a random laser with a picosecond pulse, and then using a strict camera, he saw that he could generate a couple of picosecond pulses. So that was perhaps the first generation in a short pulse. We had a work in 2017 where it had been proposed by the theoreticians that we could see replica symmetry breaking in photonic ferromagnetic media. So that would come with mode locking of the random laser. So we demonstrated this mode locking, but this was nothing that could be really applied. So more recently, the group in Universidade in Hefei, they demonstrated picosecond gain switched polymer fiber random laser, generating 600 picosecond pulse from nanosecond pulse. And this year, we demonstrated together with Jean-Pierre, who is here in the front. You can discuss with him later on. A mode-locked random laser generated transform-limited optical pulse. So that was, again, based on what we had here for our loop mirror. We had the single-mode fiber and the Erbil fiber to act as an amplifier. And exploiting the Rayleigh here as a scatter in a few centimeters of the Rayleigh, we could see the short pulse. We generated about 300 picosecond. Let me jump to the result here. We generated about 300 picosecond, and this was transform limited. So that was the first time it was generated. It can then be amplified. It's in a fiber, so it's directional, and then we can now exploit that for different applications. Finally, in my last couple of minutes, I'm going to escape all of this. This is a most recent work where we demonstrated together with the group in Henry, University of Henry. When you do was the first also is the PhD student, and this year who is the head of the group. And we observed the photonic Hall effect in photonic magnetic resistance in the random fiber laser. So the first proposal of exploiting magnetic field use random laser was by Felipe Pinheiro from Universidade Federal of Rio de Janeiro. When we say photonic Hall effect, it is related to the Hall effect, to the quantum Hall effect, to the spin Hall effect, to the photon spin Hall effect, to the light Hall effect, but there are some subtle differences. This is all in the paper. In the paper, we demonstrate photonic Hall effect, we demonstrate photonic magnetoresistance, which is, in this case, similar to the known electronic magnetic resistance. Basically, you have a diffusion equation based on fixed equation, and you have magnetic transverse scattering producing the photonic Hall effect, and you have the other term that produces the magnetoresistance. I don't have time to go into that. But the experiment is very simple. We use the polymer optical fiber with nanoparticles that are magnetic nanoparticles. They are core shell nanoparticles, silica around, and the ferrite in the core. They are very small, nanometer size. And then, if you look at what happens for the kind of measurement, one measurement we look directly at the fluorescence for the photonic magnetic resistance. We see this decreasing as we increase the magnetic field. But this experiment to see the photonic Hall effect, you have to look transversely. So very briefly, Vanderlei, please allow me to show this experiment for the photonic Hall effect, because what we do, we look at the light 90 degrees on one side and the other. We measure the two lights, and then we take the differential, and that gives you the signature of the photonic Hall effect. We then calculate the parameter that's normally used for equivalent of magnetic anisotropy, give us a number, and then we exploit also the replica symmetry break, because the photonic Hall effect affects the replica symmetry break. So again, I don't have time to go into details, but it's all in the paper, and it's all, again, explained not only with the theory, but also with hand-waving arguments, very easy to understand. And then random lasers, same thing as was said for the laser many, many years ago. It's a solution looking for a problem. Bring the problem, use random laser to solve it. It's scientifically mature. It's a photonic platform for many, many applications. Technologically, it's on this way. Lots of potential for applications. So what's next? First thing, we need people. We need bright students. We need hard-working students, postdocs, and so on. What's next in terms of science or scientific advancement? We need more electrically pumped development. We need real-life sensing applications. It's time for that. We need scalability. We need to go with random laser into the quantum world, and we have already done some initial work on that. We have done again using the same polymer optical fiber, exploiting deep learning-based studies with random laser for application for secure key generation and distribution. So this is again, just moving a little bit into the quantum world, and I'd like to finish with thanking all of you, and shining light is always something very important. Let me play this for you, and then we can go for lunch. It's not playing. Okay. That's why I wanted to use my Mac. They said I have to use mine, so too bad. The best part of the talk you are missing. Thank you very much.
Thank you, Anderson, for the nice talk. 2 talks in one. Random and Hall effect with photons. So it's open for questions, and I'm gonna go here and then there.
Hi. So how do you decide in the experiment how much disorder you put in before you see the lasing?
Sorry, say it again.
How much disorder you need to put in before you start seeing lasing?
Yeah, so it depends on the kind of system that you are using. When you use the nanoparticles, first we did it empirically, where we start with very weak amount of powder, we don't see anything happening, and then we are putting the powder, and then we find the best, and then if you go with a lot of powder, you can have a quenching. So, and then after that, you can actually calculate the concentration to avoid one or another. If you do a random fiber grating, where you do the insertion of the fiber, you write a fiber grating, then again, if you know what you need for a mirror, and then so instead of having a mirror with I don't know, few percent of penetration depth in the core of the fiber, it's going to be disordered. So it acts like small mirrors, but all disordered in the fiber, right? But we can also do the calculation in case of the Rayleigh scattering. It can be calculated using the Rayleigh scattering, using that as the optical feedback mechanism, like a mirror, or a probability of having the loops, and then you can find the best to have the best output.
Just a quick question. The pulsed experiment, were you surprised that it was Fourier transform limited in terms of the spectral bandwidth and the time? Because it's a random laser, so I would expect that there's additional limitations there.
Yeah, it was not, we were searching for that. So we were hoping that not only we could measure it, but we could calculate and propose. So I don't think the word is surprise, in that sense that I would not expect that. We would expect that if we find the right way. So it's going to be harder to do that for a dye system, for a powder where we cannot control very much. But in the case of the fiber, with the Rayleigh, where we can calculate and control everything, I mean, was a matter of finding the surprise in the sense I don't have another word, so we were not, perhaps, Jean, do you have another word? Not a surprise, but was a good result, a good achievement. It was to find the right place, because I was always looking for that, but all the other short pulse laser, random laser that we have, they are not transform limited, because we could not control as yet.
Anderson, thanks. I have a question that's connected to that in a way, which is frequency carrier in on the random laser. Can you actually measure this frequency carrier envelope offset?
By laser, because once we have it modeled, we can have the information there, and then I think we can do this. That's what we were asking. Can we measure the laser? No, because when we have remember, we have the SOA that we are locking, and we know where we are locking into the fiber, the little piece of fiber. It's like we have this mirror here, but then next maybe we have another one, but we can lock, and perhaps we can measure this phase, as we do in a mode lock laser, doing some autocorrelation or autocorrelation to the next one, and so on and so forth. Yeah. Yes, we know already there is a correlation. So, but to do this measure, we did not do that, but can be done. It's good work for the next student.
Okay, there is a few more questions. We can leave it for the lunch. We can invite the Anderson to have a lunch, a talk. In fact, you should explain everybody during the lunch why is the random laser unique. What are we going to solve with the random laser that we cannot solve with the traditional laser? That would be nice for this community. So we are closing. Let's thank you, Anderson, again. We have 1.5 hours for enjoying the lunch. Please carry your guys you want to talk with. I'm going to take Professor Agarwal and Randy in my limousine, and then many people from our group will be walking, so you can join the